So good morning, everyone. Yes, it's working. I'd like to thank the organizer for the complete semester with its many events and for this invitation today, where I chose to talk and to present you an overview of shape representations as kernels, varifold, and oriented varifold. So the two first objects have been introduced by Johan, who is in this room, 20 years ago. And varifold have been introduced by Nicolas Charon. And more recently, we present with Nicolas Charon and Benjamin Charlier common framework for all this concept of shape representation by distributions that encompasses kernels and varifold. So I thought this was a good opportunity today to do some recall on the basic properties of this object, since they are more and more used in the application for medical image analysis. Okay, so the part on oriented varifold will be joint work with Nicolas and Benjamin, but the talk will cover much more work from different people on this object. So I was a bit optimistic when I wrote my abstract. So there's still slides for a second part, but I do not expect to go that far. Today I really want to focus on the kernels and varifold. And I will start with an introduction of the context centered on computational anatomy, but I invite you to adopt for the main part of this talk maybe more a broader view with application, for example, for computer vision. So the deformorphic framework, or shape space, or large deformation model has been introduced and studied for the last 30 years now by all these nice people. And the idea is to compare shape through deformation. And two shapes will be similar if the quantity of deformation required to align them is small. So if you are given, nope, I don't know if it's on. It works. Okay. So if you are given a set of shape with no structure, no evident structure, but you have the action of a group of deformation equipped with a metric, you will induce this metric on your shape with this simple definition. The distance between the two shapes is the minimal deformation required, so the distance between the identity f and the deformation to align the shape S0 on the shape S1. So the question is how to build such group of deformation, and the very nice idea is to embed all these shapes in a common ambient space. Then you just have to define a group of deformation on this fixed ambient space, and you adopt a Riemannian viewpoint where you use a Hilbert spectral vector field to play the role of the tangent space at the identity of your group G. Then you can compute continuous path of diffeomorphism by integrating some time-varying vector field. And the distance between the identity and a vector field is the length of the minimal path. And this length is evaluated by the energy of your time-varying vector field. And so this approach allows to handle a large type of data because you just have to assume that your data are homogeneous under an action of a group once they are all embedded in a fixed ambient space. So you can manipulate curves, surface, cloud points, and a lot of other objects. And the also strength of this approach is that it combines the definition of a distance between shape with shape registration. So to compute the distance, you have to align your shape. And also, when you register your shape, you actually computed a continuous path in your space of shapes from the target, from the source to the target. Now, in application, we will deal with inexact matching problem. So you don't look exactly to reach this target S1, but you look for a deformation that brings you close to this target with respect to a metric that you want to define. And this new minimization problem can be, so this new problem can be written as an optimization problem where you minimize an energy that penalize your deformation and the similarity between your deformed shape and the target. So what metric and what shape representation? Well, this is where you use currents and varifold. So as I said, currents have been introduced in 2005 by Joan Gonès and varifold by Nicolas Charon 10 years later. And the use of reproducing kernel of Hilbert spares leads to various types of data fidelity metric between shapes that do not involve the parametrizations on these shapes. And today I will present you a common framework from this object where the choice of the metric reduces to a few scalar functions. So some related work. Johan will later talk to you about normal cycles. And Jean Fédy, from these last 2 years, have been studied the bridge between large deformation model and optimal transport. And yesterday we have this talk of Anuj on square root velocity representation. And I guess the main difference is that the definition of current and varifolds do not involve the parametrization of the shapes. Okay, so let's come back to some very basic question. Given a function f, how to define a robust evaluation of the function in some point. So the first thing to do is to evaluate the point. But if your function is a bit irregular, what you can do is compute an average of this function, so an integral on an interval centered on your point. And if you go further, you can weight this integral and so have a decrease in weight as far as you get away from your points. And all this approach are related to the integral of your function f. Again, some kind of test function. So here an indicator function, and here a smooth version as the indicator. And this gives you so some local information of the function f using an average of this function. And the properties of your estimation will depend on the properties of your test functions. And the main parameter you can think of, for example, for a Gaussian distribution, is the standard deviation, or for a more generic distribution, the shapes of the tail. So the scale will tell you how much information you take at the close neighbor of your point, and the tail will tell you how much far you also take information in your averaging. And we can generalize this concept for shape representation. So what we just talked about is you consider a function f, a set of test functions, and the integral of f to get this test function is just the linear form, the distribution associated to f. And if you generalize this for a shape x, you consider a test function that you will integrate on this shape. So the distribution of the function f applied to a test function, a generic test function omega, is just the integral of this test function on your function x. And the introduction of reproducing kernel Hilbert spares consists to integrate a kernel that will allow you to define a Hilbert spared of test functions and a Hilbert spared, the dual space of distributions. And the nice property here is that you have an explicit formula to go from your Hilbert, your dual, to the space with your kernel. So if you consider two shapes x and y, the scalar product between the two representations, the two distributions, is given by the scalar product of your two test functions phi x and phi y that I will explain, and you have an explicit expression and a very visual and understandable expression for the scalar product. So let's start by the simplest shape. You consider a point x0 in Rn. Its distribution will be denoted in this talk by the Dirac at x0, and the canonical isomorphisms that go from your space of distribution to the space of text functions give you the canonical element associated to this Dirac, which is just the translation of a generic test function that you, so like here, you had the, once you have fixed a generic test function, you could apply it at any point by just a translation, and the idea would be exactly similar here. And so why do we have this scalar function when I talk to you about kernel? Well, this is because you want to define a metric that is equivariant to rigid motions. This means that when you have two shapes and you apply the rigid transformation, like a translation or rotations, you don't want to change the distance between the two shapes. And this implies that you can write your metric as a scalar function of the distance between the 2 points. So when you compute the scalar product between two Diracs, so the distance between 2 points, it's just given by the Euclidean distance filtered by your function 5. So imagine that you choose a Gaussian distributions. You have its scale here, and if you consider now 2 points in the space, the distance between these 2 points with respect to this test function is very close. So here, your distance is close to 0. Once you reach the average shape of your distribution, for example, so on this distance, the distance would be close to so the scalar product between the two Diracs is about half, and the distance is also about half. And then when you reach so this distance, you are at this range of the point x0, the distance between 2 points is now about 0. And the particularity is now is you can go as far as you want after this limit, and the distance is always 0. So your new metrics do not discriminate the Euclidean distance after some threshold. So now you can generalize to the complete shapes, and the distribution associated to a shape y, when it is applied on a basic test function phi center at x0, it integrates the mass of y weighted by this test function. So here you have this blob that represents a Gaussian kernel, and the idea is that you will integrate the mass of y in the neighborhood of x0. And it will be weighted by, so you see that you have a decreasing intensity of color. This is the weight given by your test function. So the mass of y here is not integrated in this neighborhood of x0. And then you just have to say that two shapes x and y are similar around x0 if, when you integrate the mass of y in this neighborhood and you integrate the mass of x in this neighborhood, you obtain the same answer. So you have locally the same amount of mass in this small fixed neighborhood. And so when you, earlier I present you how to get some information in a local point of f, but you can shift your filter along the support of your function to give information on a local other point, and you can apply this exact same sliding of your filter window fx around all the points of your shape x. And so the distribution associated to the whole shape x is just the sum of all this local filter centered on every point of your shape. And now when you integrate the mass of y along this complete shape, you're just doing the integral on y and on the x of the Euclidean distance between any pair of points, but filtered by your test function phi. And you have this symmetric formula that exactly corresponds to the scalar product between the two distributions, or the scalar product between the two test functions associated to x and y. And finally, the square distance between the two shapes is the norm associated, the square norm associated to the scalar product. And what does it do? You integrate the mass of x against y, you integrate the mass of y against x. If you find the same quantity, the shape are similar, you symmetrize this process. And if all quantity cancels, the two shapes are equal or close. So how do you go to discrete shape? So in practice, when dealing with curved surface, you have polygonal line or triangulated surface. So I will call a face either a segment of your curve or a triangle or a surface. And you can define the scalar product between two faces. So the faces x, y, xi for x and yj for y. And the scalar product between these two faces is just the integral on each faces of the Euclidean distance of every pair of points weighted, filtered by your function phi. And so you can approximate this integral. The idea is that if the diameter of your face here is small, with respect to the scale of your distribution, so if you're a neighborhood where you stay close to 1, you can approximate all these points by the center of your faces. So this is what we do, and once you have done this approximation, you can replace the integral by just you obtain the mass, so the length in this case, and you apply exactly the same approximation for the face yj, and you obtain this very simple formula. Now, you can, by linearity, extend it to the complete shapes, and the scalar product between your two shapes is just the double sum over the center of all your faces and weighted by the length or the area of each faces. So you see that you obtain a very explicit and easy to compute formula. And so you've done two approximations, actually. So the first one was when you approximate your continuous curve by a polygonal line. So you did this approximation of Euclidean distance. And the second one was to approximate all the points by the center. But as long as all these distances are close with respect to the shape of your function phi around 0, this approximation is legit. And this has another consequences. You are actually robust to the parametrization of your shapes. To illustrate this, I propose you here two parametrization of the same shape. You have either one faces or two faces of mass half. And when you compute the mass of the first curve x against these faces x0, you obtain just the distance, so the mass of the faces is 1. The distance of the center against itself is 0, so you obtain phi 0. And if you compute now, you integrate the mass of the second curve, the second parametrization against the same face x0, you obtain the two mass, the half, and you can approximate these two distances by 0. And so to accept this approximation, you have again to ensure that the distance here that you can control by the diameter of your face is small with respect to the scale of your function phi, or how flat is phi around 0. So this metric induced the registration algorithms that do not require pointwise correspondence between shapes. This means that, for example, you can compute the registration of a curve of 100 points and a curve of 150 points. So you don't have to take into account your parametrization as long as you can control the diameter of each faces. A second property that I have mentioned earlier is that the union of two shapes is just the sum of the associated distribution minus the distribution of the intersection. And the metric that we have built here is quite robust to discontinuity. So here, when you integrate the mass of y against the union of the two segments, you see that you are not very sensitive to this discontinuity here. And conversely, if you want to discriminate this topological irregularity, you should stay for the talk of Johan that will present you normal cycles. So some property regarding the mass sensitivity. So you have here a shape y that is noisy, and you can assume that the length of y is almost twice the length of x. And then when you integrate locally the mass of y against x, you find twice the quantity of mass. And so the distribution of mu y can be approximated by twice the distribution of mu x because locally, spatially, the points are at the same position. It's just the mass, the quantity of mass that is changing. And so when you compute the difference, the distance between the two shapes, you obtain this difference amount of mass, which is the mass of mu x. So you're sensitive to noise, but this has also another consequence that I met when I tried to do some rigid shape registration, and when I tried to scale, to optimize the scale parameter for just the scaling between a child brain and an adult brain, and I used the varifold metric, and it didn't work. Because once you have globally aligned the convex hull or the diameters of a child brain to an adult brain, the adult brain is actually much more convoluted than the child brain. So once you have aligned the convex hull, you actually didn't align the masses. Because of the much more complicated convolution of the adult brain, you have more masses on this brain. And so when you try to optimize the scaling with the varifold metric, it tends to increase the scale of the children brain to balance these mass differences. So this is a quite a specific case where a varifold metric or current metric don't work. A naive question is, can you detect inclusions? And the answer is no, because here when you will integrate, so the mass of y1 against x, and you find the same thing. Then when you integrate the mass of y2 against x, you have basically no interaction between your points. If you imagine that your filter is of this size here, and you neglect this area, so you have no interaction. So the scalar product between these two parts of the two shapes is 0, and so the remaining distance, when you consider the square distance, you have the norm of this second part. And a last example on mass sensitivity that is related to this one is that if you consider two shapes of same length, but the shape x is much more convoluted than one which is widely spread and so widely flat, then the norm of the distribution of C to x is higher than the norm of the second distribution. This is because you have much more interaction between points. So if you assume, so you have your shape x, and if you assume that your filter is able to capture the convolutions, the folding of your shape x, then you will compute a lot of interaction, and you will compute much more interaction than if you consider just a flat line crossing your filter. So this is not with that consequences, but I come back on this later. A nice application that I found 2 years ago by Pietro Gori is data compressions. So they're dealing with white matter fiber bundles, and the problem of this object is that you have here, for example, in their data, they have 35,000 fibers. So these fibers are connecting the different area of the brains, and there's a lot of interest for these objects. And when you go now with high resolution imaging, you can go up to 1 million fibers. So if you have 100 point byte fibers, I let you imagine that these objects are really, really, really contains a lot of points. So you need some kind of data compression algorithms to manipulate them, to compare them. And their idea was to propose a clustering algorithm to define a group of fibers of similar fibers. And to do that, they used the distribution representation of shapes. So if they consider a fiber bundle B, which is the union of some fiber xi that are close to each other, so in the sense of distribution, you have an average fiber x tilde, whose distribution is close to the distribution of all the xi. Then when you consider the distribution of B, you can write it as the sum of the distributions of each fibers, and you obtain the number of fibers times the distribution of your averaging fiber. And so this equation, this very simple formulation is due to the linearity of your shape representation. You're able to sum distributions in your space of distributions. So to visualize it here, you have cross-section of 3 fibers bundle, and you have each dark point is the cross of a fiber, and the red circle corresponds to a local fiber bundle B. And so you can consider this weight n as some kind of volume around your fiber that is directly connected to the number of fibers included in your cylinder. Okay, so I promised you to speak about kernels and varifold. And so if you have understood everything so far, then you should be okay, because the rest is the very straightforward extension of the previous model. So why do we want to use tangent information? Well, when you consider these two shapes, x and y, and you just use your distribution, your point distribution as before, you have here the point x of the curve x is strongly attached to this part of the curve y. And when you locally compute a scalar product between the part x around this point and the part y, you have a strong answer that tells you that the shapes are similar at this position. But when you look with a global information on your shape, you see that this is not really meaningful. And when you will plug your metric in a deformation model, what you may obtain is that this point doesn't want to move, and so you will induce a distortion of this flat curve to generate this corner, and maybe even more ugly distortion here when this part of the black curve will try to be aligned on this part of the red curve. And so to avoid this problem, what you would like to have is that this point should be attracted to this part of the curve. And this is because you are able to see the tangent distribution of your shape. You see that here, the tangent distributions, every tangent space are about aligned to this line, and this is the same situation here, so you want to match those two parts of the curve. And you can go further with shapes orientations. So you have here two bunnies, and the risk here is that these two opposite sides of the two bunnies may attract each other, and so when you want to register them, it will be complicated to separate those two parts to align the two ears of the bunnies. But if you consider a consistent orientation of your two bunnies, and you take into account this orientation, then now when you compare the points and you observe that they have opposite directions, you will say that you have no interaction between those points, and so you will be able to align the two here. So how to do so? Well, if you use a curve and surface, you can model the tangent space by the tangent vector. For example, in the discrete case, you can define the tangent vector of each faces. And if you're dealing with surface embedded in R3, your tangent space has 2 dimensions, so you can more simply consider the normal vector. So for both curves and surface, you can always represent the tangent space by a unit vector centered on the center of your face. And now, mu x would be a distribution on a space of function defined on the ambient space for the position of the centers and on the sphere of this ambient space for the tangent vector or normal vector of each faces. And when you apply this distribution to such text function, you're just integrating your text function, but it just depends on these two components. So how does it work in practice? Let's consider the simple element of your new Hilbert space of distributions, 2 Diracs, and each Dirac contains a position and a tangent and a normal vector here. And so when you do the scalar product, you consider the Euclidean distance between the 2 centers, and you consider you evaluate the angle between these two vectors. So why can you reduce your new kernel on the tangent vector to a scalar function of the angle? This is again because of the rigid motions. And when you apply a rotation to vector or translation, you preserve the angle. So you can rewrite your kernel that defines your new Hilbert space as a scalar function on this scalar product. And so the idea when you compare these two shapes, if x and y are close with respect to your distribution phi, the points, the scalar product will be high, but it will be weighted by the comparison of the two vectors. And so phi will be high when the scalar product is close to 1 and will decrease when the angle is becoming larger. And so, for example, if you have 2 faces, let's say for curve, you have 2 faces that are almost centered on each other, but they have strongly divergent tangent vector, then the scalar product will be close to 0. And you will have no interaction between those points. So you just generalize now the function, the scalar product for a complete shape. And you just have to integrate over x and y this expression. And that can be, again, discretized. So you have this very simple formula when you sum the product of the mass of each face, the filter Euclidean distance between every pair of centers, and the filter of every angle between the tangent vector. And now the choice of the function gamma will define the representation type of your data. So if you consider gamma equal to the identity, you retrieve the current representation where you just consider the scalar product between the tangent vector. For the unoriented varifold, you retrieve this framework by using a kernel that is invariant to the orientation of your vector. So if you change here the orientation by its opposite side, you will have a minus, but since you consider the square of your scalar product here, you are not dependent of this orientation. So any function gamma that preserves the value when you change the orientation of one vector will give you an unoriented varifold representation. And the larger framework is to consider any type of kernel, and for example, the Gaussian kernel that defines the concept of oriented varifold. And just one remark, if you use the Gaussian kernel, the scale of this kernel does not depend on the scale of the shape, because you're just considering your evaluated angles, so no matter the scale of your shapes, the angles are always compared in the sphere of essence, so they take values between 1 and -1. So you can just fix once and for all the scale of this second Gaussian distribution. So the different properties of, when did I start?
You started at 15. So you have, 5 minutes, so 6 minutes.
Okay. So
17.
So I started at 20, you know. I think we were late. Okay, so just basic properties. The currents have this nice regularization properties. I will show you maybe more in applications. And this regularization of currents have a counterpart, is that when you have faces with opposite direction, they cancel the mass. And regarding the varifold, you have this properties that if you consider positive functions gamma and 5, then you can have a lower bound controlled by the Hausdorff measure of your shape, the volume of your shape, to ensure that you cannot have this cancellation effect of the mass. So now let's plug this metric in a deformation model, and I will show you a few registration applications to observe the differences between the different metrics. So here again you have the denoising properties of the current, and you see that varifolds are still very sensitive to the mass, so you cannot perform a nice matching between a smooth shape and a noisy shape. However, if you consider the same noise on the distribution, they're able to retrieve the similarity between this distribution. Another example of denoising with current with surface, and now the particularity of oriented varifold is that you capture much more local informations. And so when you try to match a horse on a camel, and you see that in the points when you have high curvature and difficult, so the matching is very difficult in this area, the most precise matrix is the oriented varifold. And you see here the cancellation effect of the currents. He just smashes the shapes and ignores the mass of this remaining part because the orientations are opposite. An example to illustrate unoriented varifolds. So they were introduced to deal with white matter bundle when it's hard to define a consistent orientation of the fibers. And you have here two faces that are unions of a small disjoint segment, so it would be very hard to orient them consistently. And so if you used an unoriented varifold matrix, you can perform a very nice alignment of the two shapes. So here you have another example to show you that you can manipulate in one deformation setting different type of data, so you have a surface and a curve. I talked to you about data compressions. By playing with the mass of your distributions, you can apply it in the opposite direction to do some restoration, some kind of inpainting of surface. So you have here two dolphins where we retrieve 70% of the faces and up to 95% of the faces. And where we play with the mass of these faces, we're actually able to register an ellipsoid on these two distributions and to retrieve quite almost well the initial targets, the smooth targets. I will skip the part about functional shape, I guess. And I would just come back on this mass sensitivity, and I will let Jean talk to you. You have 5 minutes to conclude.
Sorry.
So Yeah, I won't give you my interpretation. I will just need John to talk to you about one of the drawback of this matrix.
No, so it's not really a drawback. And so hello, so I'm Jean. I'm also a PhD student of Alain Trouvé. And basically I'm doing the transition to Johan Glonet's talk. Okay, so, well, in the last 40 minutes or so, Irène explained to us why representing shapes as measures is a good idea. And then, once you have measures, you wonder what are the distances that you can define between those objects. So let's say that you have two sampled measures, alpha and beta, you know, sum of some weighted Diracs on an arbitrary future space. And you say, I want to define a loss function. Well, if you open a book of functional analysis, the first good idea is to say, okay, I'm going to use a dual norm with respect to an arbitrary set of test functions. Now, which test function should we use? Well, for instance, if we are working in dimension 1, maybe you can use a function phi, which are h1, you know, which live in your favorite Hilbert space of continuous functions. Then, your constraint, phi square for h1 is smaller than 1. It's basically here you say, okay, so this is the L2 norm of phi plus the L2 norm of the derivative. And then you say, okay, I'm going to write this in Fourier domain. So I'm going to end up with an integral of 1 plus omega square Fourier transform of omega. And then the idea that you know is to interpret this as a factor 1 over k hat of omega, where k is a function whose Fourier transform is given by 1 plus omega square. And so in other words, k is an exponential kernel. Okay? So this is to say that when you do the standard theory of Hilbert spaces, you end up with those kind of formulas. And the crucial result of RKHS theory is that this optimization problem has a closed form solution. Basically, the good test function is nothing but a convolution of your input measures. And since you're working with discretized measures, you can expand this formula as a huge double sum. Now, this formula, it has many interpretations from machine learning and all that. But personally, I would say that when I see this formula, and since I've done a bit of physics, I recognize an electrostatic energy. Okay, why is that so? Well, that's because this is exactly the formula that physicists end up with when they consider a set of particles xi with charge plus alpha I, yj with charges minus beta j, and a Coulomb potential in k of xy. Okay, so why is that a good idea? Well, because the gradient of this energy, which is what you actually use when you do registration, is nothing but an electrostatic force that you can interpret. So let's pick a typical example. Here, I have my source distribution that I try to register on this target distribution. Both of them are sampled with 10,000 points. Now, because you know that basically you're doing electrostatic physics, what can you say? Well, you know that those particles have a plus charge. So for instance, this particle is both attracted to the negative charge and repulsed by the other positive ones. So you know this particle is definitely going to go in this direction. But unfortunately, those particle spheres are attracted to the minus charge, but are also repulsed by the other plus. And so what happens when you use kernel norms for shape registration applications is that you have basically screening artifacts. So here, I just let the particle flow with the electrostatic force, and I get those kind of results. Okay, and why is that so? That's because the particles here are shielded by their neighbors. Okay? So it's a huge problem, and basically this means that kernel norms can only be used when you have when the shapes are close to each other. Otherwise, you have to overblur everything, and it's not what you want to do. Now, can you go beyond? Yes, you can. Okay, and the idea is that, well, if you reopen your book of mathematics, and you say, well, how can I go beyond kernel norms? Maybe you just have to change the set of test functions. Okay, and for instance, you know that optimal transportation costs, they are defined as dual norms with test functions living not in a Hilbert space, but in, for instance, the set of one Lipschitz functions. Okay, so those kind of distances, they are very appealing because you know that you will always retrieve global translations. Okay, if your shapes are not well registered there, you know that you're going to retrieve the translation and local deformations. So basically, you avoid the shielding artifacts. But the problem is that it's supposed to be super expensive, right? Now, fortunately, there are good heuristics, good approximations to compute optimal transport distances. The most famous one, it's entropic regularization, which dates back from the work of Schrödinger and was rediscovered several times in physics, computer vision, and recently in machine learning. What this means that, okay, in the last 5 years or so, we've all rediscovered the wheel several times. But since 2017, basically, at the intersection of literatures in computer vision and machine learning, we've seen a lot of progress. First, and this is why Irène invented me, you can generalize optimal transport to varifolds and normal cycles and all that. Second, now we have good statistical guarantees on what we're doing when we sample the measures. Third, we can actually control the approximation that we make with the Synchron algorithm and all that, and guarantee that the loss function that we define are actually positive definites. So this means that your loss is always such that loss of alpha beta, it's positive, and null if and only if alpha is equal to beta. And finally, we have super efficient multi-scale schemes which allow you to actually use it in practice. So to come back to my example, if I use an optimal transport loss here, I'll get a high quality gradient and basically get this kind of trajectory. Okay? And the good news is that basically you don't have to code it by yourself. I did it, and I released it yesterday, basically. And so if you go on this website, you'll have access to a really top state-of-the-art implementation of optimal transport. Most importantly for those kind of problems, which use all the nice tricks that were developed in the last 10 years or so in the literature. And what you get is that now, if you have point clouds with 100,000 points, 100,000 points in the source, 100,000 points in the target, computing this kind of high quality gradients takes about 1 second. Okay? And to do that, basically, I leveraged the KEOPS library that Johan and myself and Benjamin Charlier developed, and that Johan is now going to present. Okay.
Okay, thanks very much.
And for the sake of time, and because the transition is immediate with Johan's talk, we're going to leave the discussion at the end of his talk. So thanks again, Irène.